Okay, I'm gonna start. Congratulations, we've made it to the last lecture. You've made it to the end of the semester. You've survived. And we've covered a lot. I hope you guys feel like you've covered a lot and learned a lot. You learned how to code. You learned how to do dynamics. You learned how to do linear algebra. You learned how to do statistics sort of this week, maybe today. Yeah, today's lecture, I think, might be on the short side, though I say that, I'm never really sure. There's a couple big concepts that we're going to go over today that are pretty important. And today's going to be mostly conceptual. I'm doing one math thing on the board because I think it's kind of fun to see and ties together some concepts you guys should be familiar with. But for the most part, today is going to be conceptual. And the concepts that we're going to go over today, in particular the concept of optimization, will be used in sort of your final assignment, which we're sort of hoping is going to be sort of a more fun, just kind of longer exercise set, and you'll be able to go to the TA sessions working on that. So, and it's going to sort of tie in the concepts that I'm going to go over today. I think the concepts that we go over today, you're, other than the final assignment, also likely to encounter in some form again. So hopefully the words I'm using and the concepts sort of sticks in some sense, or at least when you see it again, you can think back and it will feel less unfamiliar. I have found personally the biggest barrier in mathematics often, or the biggest barrier in statistics, is simply familiarity. People using words that you don't know can sometimes make things feel way more overwhelming than they need to be. So hopefully I can just get you guys used to some lingo and some concepts, and then when you ever encounter the math again, it's just you have that much more confidence sort of knowing broadly what's going on. Great. So what we're going to go over today is I'm going to recap Bayes' rule again. I'm going to do this by reintroducing the pieces of Bayes' rule and sort of reinforcing how we do statistics, and in particular, I'm thinking about statistics in a Bayesian framework. And this form of statistics, again, is quite common and uses sort of the pieces of the rule, of the formula we went over last time, and sort of each of those pieces is important in its own way, and we're going to sort of reiterate that and why each of those pieces of Bayes' rule is important. And we're going to use Bayes' rule as a way to understand the process of optimization today, and we're going to focus mostly on what's called a maximum likelihood estimate, or optimization of a likelihood function. And in order to do that, I'm going to have to give you guys a couple more mathematical pieces you haven't seen before. This notion of statistical independence, I think that will be pretty intuitive. And we're going to also sort of reinforce what a Gaussian distribution is. I know I've mentioned it a few times, but we'll go through it one more time. We'll use those pieces to understand optimization in a likelihood framework, so sort of in a Bayesian framework. And then I'll give you guys some concepts as to what we mean about when we talk about optimization, why it's sort of so important, why there are there's so much energy these days being put into the question of optimization and figuring out how to find, say, parameters given data in a fast and efficient way. This is sort of a huge, probably billion-dollar industry, literally. I mean, a lot of big machine learning companies are highly invested in this question of optimization, and it's sort of really important in all fields. Okay, so let's start with Bayes' rule. I'm going to recap the formula you guys have seen before, only this time I'm using theta and x. Okay, x we can consider in this context data. Theta we can consider in this context model parameters. So often the goal in Bayesian statistics is to observe some data and understand something about model parameters given that data. So all of these P's are probabilistic relationships. They'll have some functional form. It can be a variety of functional forms. They're all going to be described by theta, as I mentioned on Tuesday. And theta can be different for different kinds of P's. Theta might be one thing. It might just be a mean parameter, for example, or theta might be 3 or 4 things, describing some complicated shape. Or it could be 100 or 1,000 things, describing some complicated neural network or something like this. But in general, you can think about all of that in this framework. Each of these pieces of Bayes' rule has a name. We call x given theta, or data given the parameters theta, the likelihood. The prior is sort of what we talked about at the end of last lecture. You can think about the prior in a couple different ways. One way to think about the prior, which is sort of the most intuitive ways to think about the prior, is what do I know about my model parameters going in? If I'm measuring heights of a population, I don't expect the average height to be -1 foot. That doesn't make sense. I also don't expect it to be 100 feet or something wildly outside of the range of possibility. I can take that sort of knowledge, incorporate it into some sort of prior distribution over what I expect the parameters of my model to be. That's P of theta. If I have both of those relationships, I can generate a posterior, which is useful for a couple of reasons, which we'll sort of talk about, but one of the reasons it's useful is this gives me some uncertainty estimates over my model parameters. This is now a probability distribution over theta. So now, if I have some model, and I used the Bayesian framework and I incorporated some prior information about model parameters, I might be able to calculate a posterior and say to you, well, we think the mean of this distribution is some amount, and here's exactly how uncertain we are. Here's our probability distribution sort of describing our confidence or our likelihood of what that parameter maybe truly is. And if you have all of these pieces, you can compute what's the most challenging part to compute in Bayesian statistics. This denominator here, P of x, what does that even mean? Probability of your data. It's kind of complicated, and we're not going to focus on it too much, but I want to make the following claim because it's important for the following reason. Again, this is called the marginal distribution. I showed you guys last time we consider marginals when we have a joint distribution over two parameters that we sort of squish that down over one parameter. That's the marginal distribution. In this case, P of x is considered our marginal distribution. And what does P of x, the probability of x, even mean? Well, last time somebody brought up the insightful point that I have to make a choice when I describe, say, P of x given theta. I have to say something. I have to say it's a probability distribution that's Gaussian, or it's a probability distribution that has some other form. So how can I possibly compare models if I chose a different form of a distribution there? One of the ways we can do that is by looking at the marginal distribution. What's the probability of that data given any kind of model and any number of parameters? Basically, I choose some set of models for P of x given theta. And one of the ways to compare, if I did this with one model and another model, is to look at their marginal distributions. And the one that is bigger means the data was more likely under that sort of general model framework. So that's why that's important, but we're not going to go through any specific mathematical examples of that, but basically P of x can be used to compare across models. As I sort of mentioned, this marginal distribution can be challenging to calculate. Sometimes it's difficult to figure out all of these forms exactly. So one of the ways that we simplify this expression is we eliminate that denominator, the marginal distribution, because sometimes it's a pain, and we consider the relationship as proportional to. So I've got this funny little symbol here. You guys may have not seen this before. It did come up in last lecture, but I'd like to mention it. All this means is we said the posterior, if we ignore the marginal, this denominator, is proportional to the likelihood times the prior. So there's some scale factor that's different there. It's divided by some wrong amount, but again, we know certain things. We know that we can take probability distributions and figure out ways to normalize them, to add them all up and divide by that total amount. So there are tricks to get around this sort of thing, but if we eliminate the marginal completely, we are left with this proportional to relationship, and sometimes we just use that, and we'll use that today for conceptual explanation of sort of what goes on when we think about Bayesian statistics. Okay. So I'm going to give you guys one more probabilistic rule that we're going to use as a piece to understand how we can actually make one of these estimates, how we can actually take data and make an estimate of theta today. And this is about statistical independence. This is actually pretty intuitive. So I'm going to define statistical independence. Events x and y are independent if the probability of both of them occurring is equal to the probability of one of them occurring times the probability of the other. So statistically independent events are like most of the simple probability events that we first encounter when we encounter probability. If I toss a coin once and I get a head, it is statistically independent of the second toss. So the probability of heads is the same as the probability of heads once times the probability of heads a second time. When might that not be true? Well, that might not be true in like the figure I've described here on the left side. As I change the value of x, the probability distribution over y changes. So it's not statistically independent. Something that's statistically independent actually looks like this. So no matter how I change x, the expected value of y does not change. Another way of writing this is p of y given any value of x is the same thing as p of y. Doesn't matter what happened with x. So if I tossed one coin, I called that my x, and I tossed a second coin, it didn't matter what that first toss was. Probability of the second toss is characterized the same way. That's all we mean when we talk about statistical independence. And this allows us, the reason this is important, is if I have a ton of things, like say I observe 100 different things, and they are all statistically independent. This might happen a lot. I observe 100 coin tosses. Or I measure from a population some statistic of that population. I might consider all of those measurements independent from all the other measurements. They sort of happened in any order, and I sort of acquire them randomly. If that's true, I can take the probability of all of those events as a multiplication of every individual event. That's why independence is important. When data are independently drawn, I can decompose a ton of those data into probability that one happened times the probability that another happened times the probability that another happened, and so on and so forth. Great. And another way of saying this is all the conditionals are the same. Doesn't matter where I draw a line, provided I normalize this properly, that conditional distribution given any value of the first outcome will be exactly the same. That's statistical independence. Okay. Is that clear before I move forward? So, yeah.
Why did you multiply and not add?
Why would you multiply and not add? So the rules of probability would not work. Well, for one reason, the rules of probability don't work if you add. The probability of getting a heads, the sequence of heads, couldn't be 1/2 plus 1/2. That would give me 100% probability I get heads, and coin tosses. What's a good intuition for why they multiply them? Oh, so you have a good intuitions here? Why probabilities multiply? You think of them as trees. Okay.
I'm just going to say that you line them up this way, you line them up this way. It's all the cross possibilities.
Yeah. Yeah, all the cross possibilities. So if there's... Yeah, exactly. So so if I have one thing happen that had a very low likelihood, and then I have another thing happen that has a certain likelihood, say it's 1, the total, all of those events happening together would be low, right? Because the low likelihood, it would be times the second scenario. So, yeah, I think, yeah.
That makes sense.
2 unlikely events are really unlikely. They're not more likely. That would be adding them, right? Yeah. Okay. Any other questions? Okay. So again, the goal of today is to think about how we observe some data. In this case, I've called it M. Sorry, I think I switched notation a few times. We can think of M as X. M as X here. So I observe some data M. So I have some model, right? Models described by parameters. That parameter generates some data M. My goal is to now use M to estimate the model parameter. Okay? We call functions that take in data and estimate a model parameter estimators. Okay? So we can have a variety of different kinds of estimators. We're going to be talking about 2 of them today. But they are functions that take in data and give me a guess as to what the theta was. Now, why is this important? If I only have one example data point, or two example data points, my guess as to the probability distribution that generated my data is probably going to be pretty bad. If I wanted to understand a distribution that looks sort of like those data drawn from a red dot, and I only had two data points, and maybe they just both happen to be on the right side of this description. In this case, I'm saying like neuron number and spike count or something, but it doesn't actually matter what it is. If I draw very small samples of data, they may have been unlikely draws, especially if it was only one or two data points. So my estimates of my probability distribution, given those small amount of data, might be a bad estimate of what the probability distribution actually looks like. If the mean height of a population is, say, something like 5'8", and I use two examples, and they both happen to be 6'4", I might estimate the mean height of humans is 6'4", but of course that would be a bad estimate. So as I gather more and more data, my estimates of the actual distribution governing the data become more and more confident. Okay? But the estimates are never exact unless I have an infinite amount of data. And because they are never exact, I put a little hat over my theta. So in the literature, when I have a guess of my model parameters given some data, the sort of standard way of denoting that guess of the parameter, as opposed to the true theta that governed the true distribution, is to put a hat. Then I know it's a guess. I inferred that from the data, and it might not be exactly right. Yes?
So if you're using your model to come up with the estimate of the parameters, how do you get the model is valid?
Oh, great question. Great. So this is a hard question in statistics. How do I know if the model is a good one? And the short answer is I don't. So we can make sensible guesses, and there are reasons to make sensible guesses. But people can take the same data and model it in two completely different ways, and it's actually quite challenging to decide which is the better way to model it. Now there are certain tricks we can do, and the most famous trick is to take all of your data and throw out a couple data points. So say I take 100 people in the population, and I only look at 90 of them. And I use my model to describe those 90 people. And then I go in and I say, okay, these 10 people that are remaining, how likely is it that they are described by that first description that I made, that model? And I'll get some probability out of that. Okay? If I had a different model, a different probabilistic description, and I use those 90 and I trade on those data, and I take those 10 and I see how likely they were under the model, that's one good way to compare across models. And that's called cross-validation, what I've described. And there are other ways. Another way of comparing across models is to calculate the marginal likelihood, what I talked about before. But it's actually a challenge, and sometimes there's not super easy to do that for a variety of reasons I don't really have time to explain. But it's a good question. Great. Estimator is a function that takes data and gives me a guess of the parameters. And again, I had to have specified some functional form of P of m given theta. For example, that has to be maybe a Gaussian distribution, which is what we'll talk about today. Okay, that's just notation. Okay, so the two estimators we're going to talk about today, one is going to be the maximum likelihood estimator, and the second one is going to be the maximum a posteriori estimator. And these are both Bayesian estimators. They use Bayes' rule to define how their estimation works. Okay, they're pretty simple. So the maximum likelihood estimator is I have some data, m, that I draw, or x, whatever I called it from the other slide. I have some data x, and I want to figure out what theta can I choose that gives me the most likely description of the data. What parameters most likely to generated the data I observed? That's what a maximum likelihood estimator is. And that's where we are mostly going to focus. If I use a different kind of estimator that incorporates prior information about those model parameters, and I do the same maximization. I figure out which theta maximized that, incorporating the prior information. I am then figuring out the theta that maximizes a posterior. We'll see the differences here conceptually. With the theta that maximizes the posterior, if I have some prior information about my model parameters, the theta that does that, we call a map estimate, a maximum a posteriori estimate. I'll call them map estimates, because this is a mouthful, and that's why they're typically called map estimates. Does that make sense? So these are two ways to take data and guess theta. One way is to just consider a likelihood form, and another way is to consider a likelihood form and consider some prior information we have about the model parameters. And if we have that prior information, then we can also probabilistically describe that. Then we can generate a posterior distribution, or we can maximize basically that quantity as I search through theta, maximize that quantity, and that would be a map estimate. Now we talked about a few times in this class, and it's a really, really key point. There's one trick we always use to do a maximization or a minimization. What is that trick? How do I know when a function of a variable is at a maximum or a minimum? Yeah. Yes. So we call them critical points in the last module, that's right. But you use the first derivative and you find the special points where those first derivatives are equal to 0. We call them critical point. In this context, we call them optima. It's exactly the same thing. So if the derivative is undefined, I have a model that's really, really hard to work with. And I probably need to find some sort of mathematical trick to overcome that problem, or I need to change my model. For certainly this class, but for most research, the derivative has to be defined, at least approximately has to be defined, to do these kinds of procedures. Yeah?
You might imagine, say, models where the parameters can only take discrete values, integers, for example. And then there's no derivative. But you're still trying to do the same thing. Like you're still trying to find the parameter values that maximize the likelihood, or maximize the posterior probability. So using the derivative is just a trick that helps you do that. But the ultimate goal is just find the theta that maximizes that.
So yes, sometimes what we do, actually, if we can't define a derivative, is just check every point. It's way slower on a computer. You can check what's the probability if theta is 1. If it's discrete, for example, and I cannot move continuously, I can check the probability of theta being 1 or 2 or 3 and just pick the biggest one. But yeah, the common trick that we've used and is widely used is sometimes that functional form can be quite complicated, so we'll estimate where it's going up, or where it's going, well in this case going up, where it's going up, and we'll try to move in the direction it's increasing until we get to a point where it's not increasing anymore. Then we're like, I'm at a maximum, I'm at the top of the hill. Right? Great. Okay. So I'm going to try to go through an example of this. This is going to be the final, sort of our final mathematical example, true mathematical example of the course, at least in class. And I'm going to step through how to do this for the most common distribution. We're going to make this the simplest parameter. I'm actually only going to consider, so this is a Gaussian distribution as a reminder of the form here. And the shape of the function as I vary x is a normal curve. We've all seen this before. So the probability of x has there's some value of x where it's obviously quite likely, right? And it has some spread associated with it. This Gaussian distribution is described by 2 parameters conventionally. Okay? Those parameters, this is, by the way, over a single variable, right? I'm not considering vector or any of the linear algebra stuff that we've worked on. But the parameters describing this distribution are a mean value and a variance. Okay? So yeah, that's the form. The fact that there's this exponent e to this power and then squared, that's what gives this symmetric bumpy shape. The other thing that you're bound to see again is this distribution is used so often, and it's kind of a pain to write all of those characters out, that you will frequently just see it written, as that. This script n stands for normal distribution, synonymous with Gaussian distribution. So another way to talk about these data is they come from a normal distribution with mean equal to mu, some value, sigma squared equal to some other value. That will be the mean and variance of any data I gather. So what I want to step through is, if I am given some data, and I want to figure out, let's actually ignore the variance for a second. Let's just figure out the mean that most likely generated my data. Okay? I can set the derivative of that with respect to the mean equal to 0 and solve. And that's what we're going to do. And if some of these steps are unclear, that's okay. I want you guys to know what I'm doing. I am taking this distribution, I'm taking a lot of data points independently drawn from this distribution, and I am setting that probabilistic representation, the derivative of that with respect to the parameter I'm interested in, which in this case we're going to make it the mean. If you do this for something like the variance, it's a little bit more complicated, but it's still totally doable. We're going to set the derivative of that probabilistic representation with respect to the mean equal to 0 and solve. Okay? Solve for the mean parameter, mu, as a function of the data x. Okay, so let's say that again in math notation. So let's say I have the data independently drawn. So the likelihood I got x1, so some height in the population, some firing rate from a neuron, whatever you want, times the likelihood I got a data draw x2, times the likelihood I got a data draw x3, etc., and multiply all of these probabilities together. That's my probabilistic representation of all of my data. There is a notational convention that you guys may not yet be familiar with of how do I multiply lots of things together. It's the multiplication analog of this symbol, which is the sum of lots of things. And it's a big uppercase pi. So let's look at that. The likelihood, I draw n data points, n examples of x, under a distribution described by two parameters, we're only going to focus on one of them, but described typically by two parameters, mu and sigma squared, is equal to a multiplication of all of those Gaussian distributions multiplied together, because these are independently drawn. The likelihood of one did not depend on the likelihood of any of the other data points, the same way the likelihood of height in the population does not depend on anyone else's height. Does that make sense? What else do I have here? So we wish to find the parameter that maximizes p of x given theta, where theta, this confused me for like 6 months in college. Theta can be a variety of things. Theta is a per model representation. Theta could be mu and sigma squared, and typically in this case is. Okay? I'm going to say, for simplicity, let's ignore the sigma squared and say it's known already, and we're only going to consider theta to be mu. That's totally appropriate to do. Theta could also be 10 things or 100 things or 1,000 things. In this case, it's going to be 1 thing. So theta is just mu. So we want to find the mu that maximizes this distribution. P of x is not just one x, it's n x's, okay? Is everybody okay with this? P of x is all of my data. So we take the derivative of this with respect to the model parameter that we're interested in this case mu, and we set it equal to 0 and solve. I think everybody's okay with that. There's one more trick that is incredibly common. In fact, it's always used when we run into this kind of context. I'm going to say always. Basically always used. Instead of dealing with this probability distribution in the current form, we do a trick that makes the math a lot easier to deal with. And there's more reasons we do it than that, but we do a trick that makes the math a lot easier to deal with. We take the logarithm of that entire thing. So instead of maximizing the probability, we maximize the log probability. And that offers a huge convenience. Because now that things that were multiplied together become added together. And another huge convenience, anything that's in an exponent falls right down because it's a log. So our math greatly simplifies. And another reason this is useful, if I had a lot of data, I have a really, really small probability, like infinitely small probability, but I have a small probability associated with each one of those data points. Well, if I have 100 data points or 1,000 data points, that becomes really, really unlikely to represent inside of a computer. The number gets real small, real fast. If I take the logarithm, there's actually better numerical control too. There's a lot of reasons we take the logarithm here. There's computational reasons we take the logarithm here, and there's also just, it's way more convenient for the mathematics. Okay, so let's go through doing that. So here I have the original form, and these are going to be for all my data points. Okay? And now I'm going to take the logarithm of this expression. This multiplication becomes a sum. These two things are multiplied together, so that can also become a sum. If some of these math steps you are lost on, don't be too discouraged. Because, well, you won't be tested on them practically, but also I think the concept's way more important. Because it's getting to be the case, actually, as we move more and more into the future, that computers do all of these steps, and the real thing is, how do I test models, how do I optimize, how do I optimize well? And increasingly we're hidden from these kinds of analyses. The same way you learned how to long divide in elementary school and you haven't used this. So, okay, so this is a log times an exponent. So I can actually cancel those expressions. Log of e to the power is just that thing, just bringing the power down. These are natural logs, if that's unclear. So base e logs. Okay, now I've taken an expression that was a multiplication of a lot of different exponents into two sums, this sum over this first term and this sum over the second term, where I dropped the exponent here. Okay, doing everything right? Yeah. So I told you guys, I'm only interested in the derivative with respect of this with respect to one of my parameters, mu, not sigma, for the simplicity. We could have done it with sigma, but I'm doing a simple example, just mu. Okay? We know the derivative of something that doesn't have, that just a constant with respect to the thing we're deriving goes to 0. So this first term does not have a mu in it. So if I take the derivative of this and set it equal to 0, I can ignore this first term. Everybody okay with that? We've done this before in this class. So let's get rid of it. So now what I'm interested in is taking the derivative of this expression with respect to the parameter mu of this setting that equal to 0. Okay? Another trick I can do. I could take this out because it's 1 over sigma squared plus everything. So this is just, well actually, it's even simpler than that. I could multiply each side by 2 sigma squared. So I can drop this final term. Still equal to 0. Right? So then I have the following. I have the derivative with respect to mu, it's getting much simpler, of this expression equal to 0. Okay, now what's the derivative? We have to do a little bit of chain rule here, if you guys remember. And if you don't worry about it, just trust me. It's not worth spending too much time on. Minus 2 xn times a negative 1, because I have to do the chain rule. So I bring down the 2 and then multiply by the derivative of the inside. So this minus becomes a plus. Is that right? Okay. Oh, sorry, I took the derivative. This step is taking the derivative. I get this expression equal to 0. Oh, sorry, I forgot the sum. That's very crucial. So there's a sum here, and this is also summed 1, and it goes from 1 to n. Okay? Now this is really way simpler than we had it before, right? There were all these terms. How the hell was I going to calculate a derivative? If I take the log, I can get something quite simple. Okay? This 2 doesn't matter, because I can multiply each side by 2. So now I have this expression. Or I can multiply each side by 1/2. Sorry. No. If I have this expression, I have the following. This is the big piece. So I can take this guy. This is still a sum, because all of these xn's are different data points I drew. In the second term, each time it's just going to be a mu. Right? I'm just summing mu n times. So I can write this expression as n goes from 1 to n of xn equals n times mu. I also flipped it over to the other side. I hope you guys are okay with that step. Okay? Now what did I get? Mu equals the sum of all of my data divided by the total number of data points. What do we know that formula as? Calculating the mean. Right? So I went through this whole complicated thing of looking at these Gaussian distributions, learning about model independence, there's an exponent, etc., doing all these tricks, and we got something we already knew from the beginning. Cool? So actually, when we calculate the mean of our data, when we do this in high school, and you say, what's the mean of the data? What we're doing is calculating the maximum likelihood estimate of a mean parameter of a Gaussian distribution over independently drawn data points. Okay? And you've been doing it since you were in 9th grade. You didn't even know it. Cool. Okay, so that's the one example we will go through sort of explicitly as to how I can do this. Are there any questions up to this point? Yeah.
When you divide the 0 by 2, do you also divide the negative sign? Like, is it minus 2?
Which step? Sorry?
When you're taking the derivative, you bring the 2 down so it becomes minus 2n.
Yeah, and then I multiplied by this inside negative sign. There was a little chain rule trick I did, and I didn't specify exactly, but yeah. Now you can actually do the same thing and set the derivative of this. Actually, this is another connection that I didn't know until graduate school. If you do the same trick here with respect to the sigma squared parameter, you basically arrive at why we have to do the 1 over n minus 1 coefficient up front. You know how when you actually calculate the variance, you do 1 over n minus 1? You can figure that out by doing this with respect to the sigma squared parameter and recognizing certain properties about that, but it's kind of complicated. We don't have to do it this close. But that's where that comes from. The n minus 1 comes out if you do this calculation. Yeah?
You derive it in reverse, so derive the formula for the S distribution from just...
A mean and variance? It's a really good question. So, there are some statistical theorists that deal with these kinds of questions. And there's a lot that I haven't explained, but mean and variance have other names. Sort of, they're called moments, and they're basic properties of data. If I make certain assumptions about the numbers I observe. For example, they're all real numbers. And I make other assumptions like they have a mean specified by a mu and a variance specified by something else. And I say, what's the best way to describe these data knowing only those two things about the data? You can derive that as a Gaussian distribution.
Wow.
And you do that by basically maximizing how uncertain you are, given that you know two things about your data. It's mean and its variance.
I see.
So if you say, I don't know anything else, I have to maximize how uncertain that thing is. That quantity is called entropy, how uncertain I am. If I maximize the entropy of a distribution constrained by its mean and its variance, I actually can derive the Gaussian distribution.
Oh, wow.
That's where it comes from. In fact, some of you, if you've studied physics, if you have a particle sitting alone in space, and you only know something about its position, it's described by a Gaussian distribution. It's otherwise maximally uncertain. So this pops up actually in a lot of different ways. And it has these like wonderful mathematical forms where if you take the like log of it, you can sort of collapse all these things and it becomes really easy to work with. Actually, there's a lot of, and if this class was longer, we would go into them, but there are a lot of other Gaussian things. If like you have Bayes' rule and all of your pieces are Gaussian, you can make all the calculations really easily. If you have two Gaussian distributions, you multiply them together, it's really easy to like figure that out. This all like kind of works out really nicely, which is another reason why it's used so commonly. Okay, so we're just going to conceptually go through what a map estimate is. I'm not going to do any math or explain what a map estimate is, but just to remind you, it's finding a new estimate given some data of your model parameters theta, condition that you know something prior about that model parameter. Like you have some prior information about what it should be. So this happened to me when I first learned this stuff, and it's probably happening again to you guys. The maximum likelihood stuff makes a lot of sense, and you get to a map estimate, and you're like, do you really gain that much by like incorporating prior information? And like, what do you mean by prior information? And unfortunately, there are some tricks as to why we might use this prior information that I don't really have time to get into, but besides just incorporating prior information, using the Bayesian framework has a couple other advantages. The other one, as I've mentioned a few times, is it gives uncertainty over your parameter estimates. It actually, another reason sometimes we use Bayesian analysis is as we gather more and more data, we can become more and more confident sometimes of our model parameters, and so sometimes you can use Bayes' rule to iteratively update in a rapid way, and that's one reason sometimes we think of map estimates instead of maximum likelihood estimates. And of course, as I said before, one way to compare across different model choices, like if I use a Gaussian distribution and if I use something else, if I can do things like calculate the posterior because I have some prior distribution, and then I can calculate a marginal, I can now compare across models. I actually can't do that with the maximum likelihood estimate. I just get my maximum likelihood for that theta, and then I'm done, and I don't know if it was really Gaussian or if it was really gamma distributed or exponential distributed or et cetera. Okay. So we're just going to go through sort of conceptually a simple example of this. So let's say I have some likelihood function that's described by the data actually is described, so my noise, my data, and here, x, whatever, is described by some mean parameter. So like what we did before, theta is just mu. It's the same thing, they're synonymous. Plus some noise. That noise is going to be described by some variance. I'm not parameterizing that variance right now. We know the distribution, we already looked at it, blah, blah, blah. That's the likelihood for each point. And now let's say we have a prior. And because Gaussians are so nice and easy to work with, we're also going to say that's Gaussian distributed. It has mean 0, and it has some variance around it. Gamma here. Now, in Bayesian terminology, when I have a parameter governing my prior distribution, we call that a hyperparameter. Sort of a meta parameter. And it's actually really sometimes quite tricky to learn hyperparameters. A lot of the kind of research I do involves trying to learn. You know, if you have some data, learning this hyperparameter under some model can be quite challenging. You can't do something simple like a map estimate or likelihood estimate. Those are all estimating theta and not estimating hyperparameters. Anyway, that's just, we're not going to worry about it for now. Let's just say we know the hyperparameter gamma. So this prior is governed by some other distribution that's known. That's maybe taken from prior information about the world. Maybe we just observe this. Okay, so let's just graphically visualize this quickly. So I observe some m. That m, hey, this could be anything, heights, whatever. It has mean 0, so it's not heights, it's something else. Maybe normalized. It's normalized theta. So given some theta, I observe some data points in red here. Those are different values of m. As I vary my theta, we're now thinking about this problem as a function of the model parameter theta or mu, I get different data. So if theta is 8, I get data described now with a mean of 8. This is just graphically showing something we already gone over. Basically, I can make a picture that looks like this. So before, when I showed you one Gaussian distribution conditioned on a single value of mu, I'm now showing you a two-dimensional distribution where each conditional here, each slice here, is a probability distribution with a different mean. And I vary my mean and thus vary the hump of my probability distribution from a low value to a high value, or a negative value to a positive value in this case. Okay? So this is just a way of visualizing the likelihood. So the map estimates, well, yeah, we don't have to worry about it. The map estimates conditioned on a theta are just going to be the peak of that distribution. Or rather, the map estimates conditioned on some m is going to be the peak of a theta distribution, a distribution of a theta. So this is just saying what I said before. If I pick two different values of theta, I get two different probability distributions governing my draws or my observations in the real world. Now let's think about what this looks like under the prior. Well, I said the prior was mean 0. So it doesn't matter what my theta was, it doesn't matter what my mean and my likelihood was. The prior always has mean 0, and the theta can sort of vary about that mean. Okay? So let's think about, just conceptually, how the likelihood and the prior can affect my estimates. So I have some likelihood that describes for different values of theta what my m's should look like. Or for different n's I draw, what my thetas will likely be. And then I have some distribution over my theta that sort of squeezes everything into 0. So if that theta was really high, say I draw some m values that had some very, very high numbers associated with them, that I knew in the real world that I probably shouldn't have a mean parameter value that's too high. It probably should be close to 0 from gathering more data, or this is just something I know prior to doing my experiment. I can use this description of my prior to bias my estimate towards 0. So this yellow line indicates what would have been the estimate had I had no prior, was I just doing something like a maximum likelihood estimate. But as I incorporate a prior, I squeeze the estimates of my likelihood parameters in the direction of the prior. In this case, in the direction of 0. So this is really, really useful if I don't have a lot of data, right? Because of what I said before. If I have, if I'm measuring heights in the population and I accidentally get two people who are 6'4", and I know that that didn't really make sense, I might squeeze that estimate down a little bit because I'm operating in a low data limit and I know something about what my parameters should be. You might think if you do a neuroscience experiment and you know something about the way the brain works, or the way the brain should work, that you should use that to bias the estimates of your data. This would be a way of sort of doing So you can also visualize this graphically conditioned on some data I drew. So I draw some data, M star, and I have some maximum likelihood estimate that's sort of the description of that data. But if I instead incorporate prior information, that looks like a distribution over theta that looks like this, I can sort of take these two things, multiplicatively combine them, and I get some distribution that's somewhere in between. My maximum likelihood estimate is biased on the direction of my prior. Okay? If my measurement noise is really, really high, this is just sort of a practical application of this in real life. If my estimates are really noisy, if my estimates of my parameters say mu are very, very uncertain, my prior plays a large role. So this multiplication process biases this in a very big way, in a large way. If instead I have incredibly precise data, where the certainty over my parameters is very high, my prior plays a much smaller role, and that bias becomes very slight. These are just sort of conceptually the pieces as to what happens practically when you incorporate prior information into your experiments to estimate your model. And that's sort of the conceptual pieces of what Bayesian estimation is. We're not going to get into much more than that. So we know, as I said, that the likelihood in the prior can combine to perform posterior. If I select the maximum of that posterior, I'm doing what's called a map estimate, which is different than a maximum likelihood estimate and will bias always in the direction of the prior. It will bias always in what I knew about the model before doing the experiment to begin with. That's what this says. Bayesian estimate is always biased towards the prior, away from the maximum likelihood estimate. And why do we do this? Sometimes we do this because posterior estimates, or those multiplications, that entire distribution, gives uncertainty now over the model parameters, not just over the data. And as I said before, sometimes we use this to calculate the marginal, and we can use that to compare across models. What else did I want to say? So, I suspect again that when we did the lecture on linear regression, I talked about how we talked about fitting a line, right? That was one dimension, and then fitting a plane, that was 2 dimensions. And I said, what if you have 100 dimensions? It's some very complicated linear relationship of each data you draw has like 100 components, and I want to find the weights for each one of those components. That happens a lot if I have a lot of data. If I'm Facebook and I've got a lot of data on something. That estimation is really, really hard if I don't have a lot of data, right? I think I said this during that lecture. If you have a lot of parameters in your model, you need at least as many data points as the number of parameters to get even kind of good estimates of those parameters. Unless you do something like incorporate prior. So priors can be really, really powerful. If I have a linear regression model that has a lot of weights, I might say something like, well, all those weights should be pretty close to 0, which is exactly what we did in the example before. And that can make a regression problem go from something that's impossible to something that now has a solution. To something that I couldn't do on a computer, but now I can do it on a computer. I have a model that didn't make any sense to a model that does make sense. So these priors can be really important, even though in the example I showed it might not be quite as obvious why that's important. But particularly in models where we have lots of parameters, priors over those parameters can aid a lot in our estimates of the model. Yeah.
So a prior is always an estimation of one of the parameters.
That's right. It's a distribution over the parameter itself. And it's often an estimation of all the parameters simultaneously. But, yeah, that's right. So theta might be, in a linear regression model, all of those weights that we did, if you guys remember, like B1, B2, B3, etc., I would say they are all Gaussian and all of it's equation 0. And to make a regression problem that wasn't possible now possible. Okay, so I have one more concept I'm going to get through. And that is dealing with this exact thing I'm talking about. What do you do when your model, E of data given theta, is really complicated? Again, if it had one parameter like a mu, it was pretty easy to do. I could just write it out. But if it has 100 parameters, or if it has a very complicated functional form, or if its derivatives are not defined or challenging to define, what can you do? You can do the trick we mentioned earlier. So what if we can't solve this equation? Can't be theta p of x given theta equals 0. We can't do that. Or if it's really cumbersome to do, or what if it doesn't have a solution, theta equals some function of x? This is actually analogous to what we did in the last unit, where we didn't have a closed form solution to our differential equation. Right? That's kind of a differential equation. We can't solve it, we can't solve it. So what did we do in the last unit? We estimated it. How did we estimate it? We calculated a derivative, we knew what direction to move, and we moved in that direction. So we can use the derivative-based estimation form, and sorry, it's not clear. What I mean is, what if you can't solve theta as a function of x in this frame? You still might know the derivative at every point, but you can't solve for, like what we did here. I might be able to calculate the derivative here, but I can't end up making this relationship of just mu equals some function of x. In the same way I couldn't solve the equations like in the last module. But I still knew the derivative at every point. So we do something like optimize. Optimization is the process of finding the value of theta where the derivative is equal to 0, even if you can't solve where the derivative is equal to. Even if you can't solve for theta given some function of x, where its derivative is equal to 0. So how do we do this? We follow the same process we did before. We initialize. And often, initialization is really important in practice. In this case, I'm showing you a one-dimensional example. Theta is just one scalar example. P of x given theta is some weird functional form. And I initialize it somewhere randomly. And what do we do in our estimation methods? Well, we calculate the derivative of P of x given theta at that point. Now the goal here is to always, because this is gradient ascent, you may have heard this before. Sometimes you hear gradient descent, which is just take the minus sign of this and do it in the opposite direction. But I want you guys to think about maximizing the likelihood of the model. So I'm going to ascend to find the theta that maximizes the likelihood of that theta. Okay, so I estimate the derivative. I figure out where it's increasing, in what direction it's increasing, and I step in that direction. And I get a new theta estimate. How do I do that? Take my old theta estimate, I multiply it by the derivative, and I have some free parameter here, some thing, alpha. We'll call it the step size. We did this in the last module too, right? We called that dt in the last module. Now I'm calling it alpha. That's just convention here. We're not thinking about this evolving through time anymore. We're thinking of finding a solution. Okay, so I have some old estimate, I have what direction I'm supposed to go, and I step in that direction. Now I have shown you an example where it's one dimension, it's over a scalar. Do you guys remember what it's called? When we do a multidimensional derivative, it had a special name. What was it called? The analog derivative for a linear algebraic system. We used it last module. Jacobian, exactly, right? So in this case, I'm conceptually giving you guys the direction to go for a scalar estimate, step up. Wherever the slope's going up, step up. But instead, if I have some complicated parameterization over lots of parameters, I'm going to calculate the Jacobian of that entire system. And I'm going to use the Jacobian to find a direction to step efficiently. I'm going to step up the slope as much as possible. I'm going to be, if this was 2 dimensions, I would be climbing a mountain. And I would always go in where the gradient is steepest. We're not going to go through the specifics there, but that's basically the conceptual idea. Always go in the direction that's steepest. Sometimes they will make this alpha proportional to how big that derivative is. That's really important. If the derivative is really, really steep, I can probably take a big step. If it's getting really, really shallow, I don't want to step too far. There's a lot of work actually done in this space. Like, how do I manipulate my alpha to make steps the best way? I don't want to get to the top and have my alpha be too big and overshoot and undershoot. I mean, basically the idea is this, right? I have some initial estimate, I update it with my derivative, and I step, and I get a new guess. Update it with the derivative and step, step, step. Boom, until I find the end where the derivative is equal to 0. Okay? So, I don't remember what I was saying, but basically if you get to the top up there and your step size is too big, I might go to one side of the optimum, basically step over the peak of the cliff, and then realize I should have gone back the other way. And then I step over the peak of the cliff again and then realize I should go back the other way, and I never really hit 0, right? So in that case, I'm stuck in an infinite loop. So I need an optimization algorithm that accounts for that. There's a lot of complexities of that form. Right? And I'm going to go over one other big complexity, and then we will end early. And that big complexity is here. I've shown you a picture where there's one peak. There's only one top of the mountain. And I gave you an algorithm to find the top of that mountain. Just keep stepping up until you get to a place where you're no longer stepping up, where you're flat. Okay? But what if my model, which is often the case, which is most models, looks like this? Now what might happen? Well, let's say I initialize someplace like here. What's it say? It says go to the right. Go in the direction that I'm moving upward. So move my theta in that direction. That's where the derivative is pointing me. Okay, let's do it. Boom. Oh, look I got to a peak. But it wasn't the best model parameters, right? Because it didn't maximize that likelihood. There was another peak way over here. And if I was instead at that peak, I would have better theta describing my data. I would have done better. This is a worse model. It's an objectively worse model. Right? It just probabilistically doesn't describe my data as well as it could have. This is called finding a local optimum. And this is, the terminology sort of in the literature for this is this problem is not a convex problem. So when a function has one optimum, has one place where the derivative is equal to 0, that's a globally convex function. In this case, we would call this a non-convex function. So when I run optimization procedures on a model that looks like this, given some data, I kind of am stuck. Literally stuck in a local optimum, but I also don't know if the parameters that the model spits out are the best parameters for it. I think that's all I wanted to say. Yeah. Are there any questions about this? Yeah.
Wouldn't you just continue to randomize the initial one and then
Yes. So this is exactly how, probably the easiest way that people have overcome the problem of local optimums. I run it 100 times, and then I find the best of those 100 times. Because if I did this again and I initialized way over there, I'd get some new data out, and I would actually be able to measure that PMX is higher there. I did this 10 times in this case. This becomes harder and harder as the local, if this was a 10-dimensional system, a 100-dimensional, 1,000-dimensional system, then I'm waiting at my computer for a really long time. So then the name of the game becomes how long do I wait and how powerful is my computer? So there are other tricks. Any other questions? Go. Great. So just sort of to end, this process can be quite challenging, and there can be lots of local optimums, and as a result, there are an increasingly large number of algorithms to actually optimize efficiently. And Julia, for example, has a bunch of them built in. In fact, you can load in optimization packages. I gave you one example that sort of approximation of what would be called Newton's method, which is analogous to the Euler method we went over, which is kind of also called, there are slight differences, but basically that's Newton's method of finding where it's 0. I might have some function that like doesn't have a peak, but I still want to find the best value. There are different algorithms to do this, and probably the number of algorithms that do this is like in the tens. These are some example algorithms that like different statisticians use for different contexts, and they overcome these problems of globe optima in different ways. They randomly initialize, they make random estimates of gradients. Sometimes they use the second derivative, and all of that can be hidden from neuroscientists, for example, because you can load in packages that run these algorithms on their own and find optima in cases that work well for your specific data and the specific kind of, let's say, probabilistic model that you're using. But yeah, to just sort of end, the process of optimization for probabilistic models is ubiquitous. And it's sort of the primary thing we do as statisticians to find these data, given these data. And for your final sort of assignment, our hope is that we can give you guys some data and step you through a process of finding some optimum theta by doing the procedure analysis that I just sort of conceptually. Cool? Okay, I hope you all had fun and learned a lot. Thank you guys. I don't know if Carlos has anything to say? No? All right, great.
Is the running it 100 times, is that